Hello APC Mechanics students, today we'll solve the past paper of RQ 2023 Set 1 Exercise 3. A system consists of a small sphere of mass m and radius capital R at rest on a horizontal surface and a uniform rod of mass capital M equals to m and length L attached at one end to a pivot with negligible friction, where R is much smaller than L. Now this symbol means that it's much smaller. There is negligible friction between the surface and the sphere to the right of point A, and non-negligible friction to the left of point A. So here basically we don't have friction, here we have friction, and there is negligible friction at the pivot, which means we can use the conservation of energy. The rod is held horizontally as shown in figure 1, then is released from rest, which means the initial speed here is 0, which means the kinetic energy is 0. The rotational inertia of the rod about the pivot is given by 1 over 3 ml square, and the rotational inertia of the sphere about its center is given by 2 over 5 mr square. After the rod is released, the rod swings down and strikes the sphere head-on. As a result of this collision, the rod is stopped and the ball initially slides without rotating to the left across the horizontal surface. Now this is important, the rod is stopped, which means after the collision the speed will be 0. Now in part A, they're telling us derive an expression for the angular speed of the rod just before striking the sphere in terms of the length L and physical constants as appropriate. So initially the rod is in this horizontal position, it will be released, and if we refer to the text, they're asking for the speed, for the angular speed of the rod just before striking, so momentarily before collision, and they're interested in the angular speed. And here notice carefully, because this is performing rotation, then all points of this rod have the same angular speed. For this reason, whenever they're asking us about the angular speed, they didn't specify a specific point. However, if they're asking about the linear speed, then they should specify a specific point, whether the center or the bottom of the rod. Now we need to derive the expression of this angular speed, and we know that this can be approached using two ways, either Newton's second law or conservation of energy. Newton's second law here in this case is a bit challenging because we need to utilize the oscillatory motion or the differential equation, so we can approach this problem using the conservation of energy. But before doing so, we need to specify our PE level. Now in such type of systems, the best choice would be to take the PE level to be the center of mass of the system at its lowest point. Now after the rod is being released, it will have the following vertical position before it strikes the sphere, and we will take the PE level to be the level passing through the center of mass of the rod, if this is uniform mass distribution as being stated in the text. So the center of mass would be located here, this of length L, so that would be the PE level. Now based on our choice, and the final position of the rod would be here, so the final gravitational potential energy would be 0. What about the initial? Would be just given by the vertical distance from here to here, which is given by L over 2. This is one way to do it. Another way is to remember always in such type from horizontal to vertical, the h is given by the distance from the pivot to the center, which is given by, in this case, also L over 2. Now as stated, so let's first mention, take the PE level to be the horizontal, passing through the center of mass of the rod, when in the vertical position. And now, because we need to apply a big law, we need to state apply conservation of energy. and here we're gonna say energy initial is equal to energy final, which means kinetic energy initial plus gravitational potential energy initial is equal to kinetic energy final plus gravitational potential energy final. This is 0 based on the following statement, and this is 0 because it's released from rest. Remember that the mass of the rod is given by capital M GH, and here what about the kinetic energy? We're assuming here pure rotational motion, but the thing is that I would be dictated by the parallel axis theorem around the pivot point, which is already given here, so no need to adjust anything related to the moment of inertia. So that would be half I omega square, and we're interested in determining omega square. Now that would be mg L divided by 2, which is equal to half the moment of inertia is given by 1/3 ml square, and that would be omega square. Now we can start applying the cancellation effect. M cancels with M, half cancels with half. Now power 2 cancels with L, and we're left with G is equal to 1/3 L omega square, and let's isolate omega square. Then omega square in this case is given by 3G divided by L. Then omega is given by the square root 3G divided by L. So that would be the angular speed of the rod momentarily before it strikes the sphere. Now in part B, derive an expression for the linear speed v0 of the sphere immediately after colliding with the rod in terms of the length L and physical constants as appropriate. Since it's a mix between rotational and translational motion of the sphere, then we can apply the conservation of angular momentum. Then apply conservation of angular momentum So remember, this is a big law. Then we need to mention the law that we're using. And here let me take a step backwards, and they're telling us to derive the expression in terms of L and physical constants as appropriate, as being done here. Now what does the conservation of angular momentum states? Initial angular momentum should be equal to final angular momentum. Now here the angular momentum before collision is only being possessed by the rod, which is given by, for a rigid body, I omega, and here this is omega that we have determined, which is given by 3G divided by L, and the moment of inertia is given by 1/3 ml square. Now what about the final angular momentum? So basically it's the angular momentum of the sphere around this pivot, and it's given by the mass of the sphere, which is given by m, and v0 that we're interested in determining, and the distance from the position of the sphere at the moment of collision to the pivot, and that's given by small l. Now I is given by 1/3 capital M L square, and omega is given by square root 3G divided by L equals m v0 L. Now capital M is related to small m by a factor of 2. Then that would be 1/3 multiplied by 2m L square, the square root of 3G divided by L equals to m v0 multiplied by L. Now remember that our answer should be, because we're interested in determining v, and as it seems it should be expressed as a radical, a factor multiplied by GL, because this is only the unique combination in such cases that give us the speed. So we should work on that. Now m with m would cancel. Now to the power of 2 and L would cancel, and we have 2/3 L, the square root 3G divided by L equals to v0. Now let's drag all of this inside the radical. Then 2 will be promoted to be 4, 3 will be promoted to be 9, L will be promoted to be L square. Then v0 in this case would be given by the square root of 4/9 L square multiplied by 3G divided by L. Now here 3 and 9 would cancel to give us 3, and this would cancel with that, and we're left with 4/3 GL. Then v0 in this case is given by the square root of 4/3 multiplied by GL, as anticipated. Now after sliding a short distance at time t is equal to 0, the sphere encounters a region of the horizontal surface with a coefficient of kinetic friction mu. So this is kinetic friction. Beginning at point A, as indicated in figure 1, the sphere begins rotating while sliding, so we cannot use any sense the condition of without slipping from points A to points B, because here we have kinetic friction and it is without sliding. So here V equals to omega R breaks down. So the sphere from the points from A to B is performing two types of motion that are independent: rotational motion and translational motion. The sphere begins rotating while sliding and eventually begins rolling without sliding at point B, also as indicated. So at point B exclusively we can use V is equal to omega R, only at point B. In the following diagram, which represents the sphere while the sphere is traveling between points A and B, draw and label the forces, not components, that act on the sphere. Each force must be represented by a distinct arrow starting on and pointing away from the point of application on the sphere. Now here in this case we are representing a rigid body diagram because maybe later we'll be interested in determining the torques. And in the torques we're interested from the point of application of the force to the distance of the axis of rotation. Now for sure we have the pull of gravity. The pull of gravity should be represented from the center of the sphere, like that, pointing down. So that's the pull of gravity. The normal push should be represented from the point of contact of the sphere and the surface, which is here. And it's better to represent the normal push to be equal to the pull of gravity, although they didn't state in the text that to take into consideration the relative length of the vectors. And now we have friction. Here we're talking about kinetic friction, and because the motion of the sphere is to the right, then the friction is to the left. And the friction in this case should be represented from the point of contact between the sphere and the surface, which is like that. So let me say that this is FF. Now in part D, they're telling us derive an expression for each of the following as the sphere is rotating and sliding between points A and B in terms of V0, mu, RT, and physical constants as appropriate. What does V0 represent? V0 is the speed at the point A, which is the speed after the collision. We already have determined V0 to be given by the radical 4/3 GL, but no need to use this expression. We will limit ourselves to this expression. Mu is the coefficient of kinetic friction, R is the radius of the sphere, and T would be the time, so as function of time. So the linear velocity V of the center of mass of the sphere as function of time. Here, because all the forces are assumed to be constant, and V can be determined from A, but first A can be determined by applying Newton's second law. Since we're talking about linear, then we'll apply Newton's second law. For translation, then apply. Also, let me state that we can directly anticipate that the acceleration will be given by minus mu g, so we will work on that to be dictated from Newton's second law for translation. So apply Newton's second law. For translation, and remember that whenever we're applying a big law, we need to mention the law that we're using. So what does Newton's second law for translation states? That F naught is equal to ma. Now which mass? Mass of the sphere, which is small m. Now what are the forces? We have the pull of gravity plus the normal push plus the friction. And remember that this is a vector equation. It will give the birth to two linear equations working in 2 dimensions. So let me state here projection along the horizontal. Now the pull of gravity has no projection on the horizontal as well as the normal push, so that would be 0 plus 0. Now friction is acting opposite to the direction of motion, which is assumed to be to the left, so that would be minus FF is equal to ma. So, and remember that the acceleration is not projected. The friction is given by the coefficient multiplied by the normal push, and we can say that the normal push is equal to mg, and the reason is given by balance forces. And now let me continue this here on this portion. So we have that minus mu mg equals to ma. M and m cancelled, so acceleration is given by minus mu g, but we're asked about the linear velocity. Now since the acceleration is constant, we can utilize the velocity using kinematics. So v is equal to v0 plus at. So here I'm using this one because they want it as function of time, and I won't use the time independent equation. Now already v0, it is required to be expressed in terms of v0, so v0 minus mu g multiplied by t. Then the speed as moving from a to b, or the velocity, is given by v0 minus mu g t. And here notice that it is important to represent the acceleration at the negative sign because we are talking about vector quantities and not the magnitude. Now in idea number 2, they're asking us to, again, so we read from part D, derive an expression for each of the following as the sphere is rotating and sliding between points A and B in terms of v0 mu r t and physical constants as appropriate. The angular velocity omega of the sphere as function of time t. One thing that you might do here wrong is to say that v is equal to omega r, and already we have found v as function of t, then omega can be deduced directly, and especially since this is labeled by idea 1, idea number 2, and this is completely wrong. Why? Because as we have stated and stressed on the fact that between points A and B we have rolling with the slipping, with the sliding, which means that v and omega are not related in any sense. Then the way to proceed in idea number 2 is just to apply again Newton's second law, but this time for rotation. About which point? About the center of the sphere, and this is very important. You cannot apply it at this point. About the point of contact, simply because we don't have rolling without slipping. So if we have rolling without slipping, you are free to apply Newton's second law for rotation about the center or around the point of contact. But here, since we're talking about rolling with the slipping, so we are limited to this point. Then for that, and because we're applying a big law, so let me say apply Newton's second law for rotation, and here it is important for us to state about which point, about the center. Why this is important? Because this will allow us to determine the torques properly. So let me say torque nat equals to I multiplied by alpha, and we're interested in determining alpha. Why? Because that will allow us to calculate omega, and here why we referred for rotation, because we're interested in angular velocity. Now what are the forces acting on the sphere? We have the torque produced by gravity, produced by the normal push, and due to friction. Now luckily enough, gravity and the normal push, they don't produce any torque because the line of action of the forces passes through the center. So that would cancel, then 0 plus 0. Now what about the torque produced by friction? Now remember the definition of the torque. The torque is plus minus the force multiplied by the distance multiplied by the cosine of the angle. Now here in this case, the ball will be rolling in this direction because it's moving to the left. Now notice that this force, which is a friction, provides positive torque because it will try to rotate like that. So that would be plus the force, which is Ff, multiplied by the distance from the point of application to the center, which is basically radius of the sphere, and no need to multiply by cosine anything because it is being applied tangentially. Now the moment of inertia, we need to replace it by 2 over 5 small mass r square multiplied by alpha, because from the text the moment of inertia of the sphere is given by 2 over 5 mr square around its axis of rotation, or around its center. Now remember that also in this case friction is given by mu mg. This is the same as the first part, multiplied by r is equal to 2 over 5 mr square alpha. Now m cancels with m, power 2 cancels with r, so we're left with mu g equals 2 over 5 r multiplied by alpha. And if we isolate alpha, alpha would be given by 5 mu g divided by 2r. But we're not interested in alpha, we're interested in omega. We know that omega is related to alpha using kinematics, which is given by omega 0 plus alpha t. And here we need to be very careful. Initially the sphere at So if we refer to this figure, now here, as the rod strikes the sphere, now it gives it an initial velocity v0, but till this moment the sphere has no angular speed. As it reaches the point A, the force that is responsible for start giving angular speed for the sphere is basically the friction. Okay, but the thing is that there is no direct dependency between omega and v. So let me repeat and state again. As the rod strikes the sphere will gain an initial velocity v0 and reaches the point A. But now the sphere, because here we don't have any friction, the sphere would be impossible to gain any angular speed. So at this point in particular, what does the sphere have? If we're talking about v and omega, it has an initial velocity v0 to the right, but omega is 0. So omega 0 is 0. As the sphere starts rotating, rolling from A to B, it will gain omega. But the thing is that what's the difference between gaining omega here, whether with kinetic friction or with static friction? With a static friction, there will be a direct dependency between omega and v, which is v is equal to omega r. But for the kinetic friction, v will be dropping down and omega will increase, but there is no direct relation between these. All right. So here, let me say that this is 0. And omega in this case is given by 5 mu g divided by 2r multiplied by t. Now in E, idea 1, derive an expression for the time it takes to the sphere to travel from point A to point B in terms of, so let me check here that our answer indeed is being expressed in terms of mu, r, t, and physical constants as appropriate. Now we need to derive an expression for the time it takes to the sphere to travel from point A to point B in terms of v0, mu, and physical constants as appropriate. So we need to find an equation that we can solve it in order to find the time. And this is done by utilizing at point B, we have the condition of rolling without slipping. So let me say at B, we have v is equal to omega r, which is the condition given by condition for rolling without slipping. Now v is given by the function v0 minus mu gt from the previous part, from this one, and we will replace omega by 5/2 mu g divided by 2r and we'll solve for t. So 5 mu g divided by 2r multiplied by t. So that is omega multiplied by r. Now r with r would cancel. That would be v0 minus mu g multiplied by t is equal to 5 mu g divided by 2 multiplied by t, and we're solving for t. What's the type of this equation? This is a linear equation in t. So dragging this to the right hand side, that would be v0 equals mu gt plus 5/2 mu gt. Reading it from right to left and factoring out t, that would be t into mu g plus 5/2 mu g equals to v0. Now t in this case, so let me do the common denominator here, that would be 7/2 mu g is equal to v0. In this case t is given by the double of v0 divided by mu g, and here we have 7. Then indeed it's being expressed in terms of v0, mu and physical constants as appropriate. Now in the last part, in idea number 2, derive an expression for the linear velocity of the sphere upon reaching point B in terms of v0. This is straightforward. Initially v, the linear velocity from points A to B, is being expressed as v0 minus mu gt. So it's left just to replace t by the expression that we obtained here, and it will be expressed in terms of v0. So v is given by v0 minus mu g t, which is v0 minus mu g multiplied by 2 v0 divided by 7 mu g. Mu g would cancel. That would be v0 into 1 minus 2 over 7, which is basically 5 over 7 multiplied by v0. Then the linear speed at the point B is given by 5 over 7 v0. Then that's it for me in this video, guys. See you soon in a new one.